Welcome, everyone, and thanks for joining us for this session today on building institutional trust with zero-knowledge proofs. Over the past few years, we have seen tremendous progress in blockchain infrastructure that has led to lower settlement times, lower transaction cost, and to some extent, better interoperability. And this is really paving the way for mass adoption. However, as this technology matures, we also see new challenges coming up. More specifically, trust. So how do we build trust between different parties without compromising on privacy, on security, or on compliance? And this is exactly where zero-knowledge proofs, or ZKPs, come into play. At a very basic level, a ZKP lets you prove some information is true without actually revealing the underlying information. And this is extremely powerful. And this has been long considered as a cryptographic marvel. However, what's exciting now is how this technology is actually becoming usable. We are seeing tremendous progress in performance, in developer tooling, and more use cases coming up using this technology. So at RippleX, we are also researching how we can leverage this extremely powerful tool to bridge some gaps and address challenges to pave the path for institutional adoption. And RISC 0 is also at the forefront of this shift. They are actually trying to make this technology more and more accessible to the developers. So let's unpack today what all these advancements mean for the institutions as well as developers alike. And I'm extremely thrilled to have Brett Carter, VP of Product at RISC 0, to share his insights. Welcome, Brett.
Thank you so much, Aanchal.
Awesome. Let's dive right into it. Well, ZK has been a hot topic for years, we all know, especially in academic circles or privacy coin communities. So what has actually changed recently that makes ZKPs more usable and more accessible for people?
Yeah, it's a great question. ZK's changed a ton in the last few years. I think it's developing faster than anybody expected. Two of the core innovations that come to mind that have really made ZK much more accessible to developers and gotten to the level, improved the level of performance such that we can build practical applications today come to mind. Now, the first one is actually innovations in the lower level proof systems themselves. So most ZK proof systems today are what we call Stark-based systems. They operate over prime number fields. Getting a little bit nerdy here for the developers, but a key innovation there is that there was a discovery that as you sort of reduce the size of these prime number fields, so for example, a few years ago, you generate zero-knowledge proofs over a field of 256 prime numbers, and we'd whittled that number down and down. Some of the leading proof systems today use 31-bit fields, and that's improved the performance of these ZK proof systems by roughly 1,000x since 2023. Yeah, so performance is dramatically improving thanks to those innovations and others. Another one is an innovation that we've led, which is the development of what we call general-purpose ZK VMs. So on top of these proof systems, we've created an abstraction layer that allows developers to write general-purpose applications. What does that mean? Typically, you go back to 2022, 2023. The only way to build ZK systems was through something that we called writing these arithmetic circuits. It was kind of like designing a chip specifically for an application, which you could imagine would be a very expensive and wasteful process. So for example, if you wanted to build a ZK application that proves somebody put you in check in the game of chess, you'd have to write, essentially, you'd have to tell a developer, hey, I need this application. We want to do chess in ZK. And a developer would have to figure out effectively how to build chess as a polynomial, as a math equation. And that's a really difficult paradigm or concept for the average solid back-end developer. It both required an expertise in software development and in mathematics, and there was maybe a few hundred people that could do this. Our company had a really unique insight, which is actually if we write one ZK circuit that works like a CPU, you could write programs in languages like Rust that compile down and run through this one circuit. And this allows developers to not worry about the arithmetic circuits. They no longer have to write them in specialized languages. They can just write a program in Rust, compile it down, and run it through our ZKVM, and that program inherits the power of ZK. And so this has been a really core innovation. The advances in performance have made it practical and have really made it, in our observations, over 100x cheaper and quicker to develop ZK applications.
That's great. So if I were to boil it down in simple words, there's improvements in both backend as well as frontend that is making this technology more accessible.
Yep, exactly. Performance and then the front-end developer experience has improved dramatically.
Awesome, awesome. And well, I think you already answered this, but RISC 0 is by building this general purpose compute ZKVM. Is there anything you would like to add that this technology enables that was not previously possible?
Yeah, absolutely. I think if I described sort of this paradigm shift from arithmetic circuits to general purpose programs, and some of the things you get really for the developers in the crowd that I think they'd appreciate is code reuse. This is so critical to all of the software that we build today. So in the previous sort of circuit-based paradigm, if you wanted to do something like verify an Ethereum signature, or even a Ripple transaction, or XRP ledger transaction or signature, you'd have to re-implement that signature algorithm in one of these arithmetic circuits, which could take months just to do something as simple as a signature check. In these general purpose ZKVMs, you get code reuse. And so what I mean is, like in the Rust ecosystem, which is the primary language that we support, there's a package manager called crates, and you can go there and you can find in the Rust crypto crate essentially any signature algorithm, just import that crate into the ZKVM and use those cryptographic primitives which have already been implemented. So you can imagine how this really dramatically improves developer velocity, reduces the cost of these developing these applications and such.
Awesome, and that's huge.
Yeah, really huge.
All right, so let's switch gears to some of the use cases, some of the challenges that I think ZK is extremely, incredibly important to solve and solves it really neatly. So first I would like to say that privacy and compliance. We all know that it is an extremely important, these are the extremely important features for mass adoption for institutions. However, we are well aware that these two features are inherently incompatible with each other, right? So how do you think zero-knowledge proofs, this versatile tool, can easily solve this problem for institutions?
Yeah, there's a little bit of misconception about ZK and privacy. I think most of the existing protocols today are 100% private, right? So you think of Zcash, or you think of Alio, if you're familiar with those. And you sort of think from a regulatory perspective, those are huge no-nos because they're sort of completely private. You can't see what's going on behind the scenes. Potentially there's malicious state actors at play and money laundering taking place. But really, ZK enables a primitive that I call programmable privacy. You can actually determine which information you're revealing, which information you're hiding. It doesn't have to be completely private. And so for financial institutions, being able to use this programmable privacy primitive to develop selective disclosure policies and programs that allow you to do private payments but remain compliant, that allow you to provide a cryptographic reveal key that lets regulators look into a specific transaction or find some information about it, really makes it so that institutions can both operate on public blockchains, but provide the required level of privacy that's necessary and expected due to the regulatory landscape and existing expectations.
Absolutely, I think it's extremely important. Right, like we do not have to necessarily expose the entire data, but what we can do is verify what's necessary, and that's incredibly powerful. Yeah, awesome. Another use case, one we all know, growing area of interest in ZK is for cross-chain or cross-system interoperability, and that field is like fraught with technical challenges. What role can ZKPs play in enabling trust between otherwise siloed systems, whether it is blockchains or any Web 2 application for that matter?
Yeah, this is a really exciting use case for ZK. I like to tell people I think a simple mental model for ZK is you get three things. You get scalability, you get interoperability, and you get privacy. So sort of within this interoperability domain, how does ZK sort of, what implications does it have? As we've improved the performance of these systems, roughly 1,000x over the last 2 years, as I described, all of these new interoperability use cases open up. So to give you an example, we're actually able to prove the consensus of chains like Ethereum, Celestia, soon to be Solana, and even potentially the XRP ledger. And what that means is, effectively, with these zero-knowledge proofs, if you can prove the consensus of one chain, it's almost like having the ability of running a node of this chain on another chain like Ethereum. So imagine if Ethereum could verify the state of the XRP ledger in the same way that a node would be able to verify the state of the XRP ledger. This sort of provides a new basis for trust. Currently, interoperability and bridging happens via custodial solutions, or essentially via multi-sig. And we've seen over the last few years how difficult it is to protect those systems using multi-sigs as a basis for trust. There's been billions of dollars in hacks, and while we're getting better, right, and these systems are hardening, there's this new basis of trust that's much more seamless, much more trustless, and relies on cryptography, rather than custody or trusted solutions. So I think that's really, really exciting from a blockchain interoperability perspective. I think for financial institutions, legacy software institutions as well, what's another really exciting interoperability primitive that ZK unlocks is really the ability for blockchains to interoperate with Web 2 crypto primitives. A really simple example is there's standards like OAuth that require, and it's an authorization standard developers would be familiar with, and in some cases require signatures over attested information. So for example, the US federal government has a platform called ID.me, and through their API, you can actually request information like KYC information, citizen status, things like that. And that information is signed. And using ZKPs, we can actually generate a proof of that data, attribute it to ID.me in the US federal government, and then verify that proof on-chain, allowing these Web 2 systems to be interoperable with on-chain systems.
That's something new. I didn't know about it.
Exciting.
Do you have any idea about the adoption of these systems? Like, how popular are they?
Yeah, it's funny. If you want to start a startup, that's probably a good place to do it. There are some teams, like the ZK email team. There's on Sui, there's a project called ZK Auth that are just sort of beginning to use these capabilities. Again, as performance is really just enabling them to be possible. And so I'm very optimistic that ZK will unlock lots of new use cases as we reduce the limits of compute that you can do on chain, like this and others as well.
Cool, makes sense. All right, let's talk about builders. So we're talking a lot about the advancements that ZK Tech has made, but how close we really are for developers being able to integrate ZK into real applications, and what is still missing in terms of tooling or abstraction? What's your opinion on that?
Yeah, I'm a little bit biased, right? But I think this technology is quite practical today. You can kind of think of, you want to go down the path of adopting ZK, you see some value proposition in the technology. You can kind of think of the process for that in 3 phases. There's the implementation phase, developing your ZK logic, integration, like sort of integrating it into your blockchain application or your smart contract application. And then there's the deployment phase, which is like, how do we productionize this and support it? And really, like, all 3 of those phases have been fraught with really difficult development hurdles. The ZKVM has really helped with on the implementation perspective and the integration perspective. There's still some challenges as far as deployment and running these systems in production goes. And we expect that to get easier and easier. So yeah, I think like there'll be continued improvements in performance of these ZKVMs, continue like broader language support, things like that, which will continue to lower the barriers to entry. But really today, I think we've done a great job in making this technology accessible today. Yeah.
I guess one quick question before we get into the closing question is, like, there is all this never-ending debate on whether circuit-based or general-purpose VMs are better for, I mean, obviously there are trade-offs between the two. One is good for one thing, the other is for another. But there are still challenges with the general-purpose ZKVM. As like more abstraction layers you introduce, there is more compromise on the performance. Where do you see? Do you still think, like, I guess your opinion is going to be biased again, but really, like, how do you think is it? Are there specific use cases that one is better than the other? Or do you think like it's an umbrella, like ZKVMs are the best?
It's a great question. There's still place for a sort of dedicated circuits. But what's really nice is ZKVMs have created a new development flow. Like I've personally witnessed ZK teams spend 9 months trying to implement a basic signature algorithm in a dedicated circuit. It can be very, very difficult. They're difficult to test. You imagine you make a change or you find a bug. There's a lot of other advantages to working in general purpose ZKVMs as well. But one of the things you unlock is actually if you start first in a ZKVM, we can actually, and this is like maybe a little bit new, we haven't talked about this, but if you're not familiar with ZK, but we can actually start in a ZKVM and we can identify where the overhead is at in your protocol. So for example, you're doing a lot of a particular type of hash function, and we can write what we call a precompile in the ZKVM, which is a dedicated circuit specifically for that operation. So you kind of get a best of both worlds paradigm there, where we can get a thing working, which is a really helpful development flow, and then we can optimize the performance over time by writing dedicated circuits and sort of splicing them into the ZKVM. So yeah, I think, again, ZKVMs, but there's a mix, right? There's still a place for dedicated circuits.
I like that hybrid approach.
It's great.
Awesome. All right. So my last question would be, what should builders watch for from you over the next year? That's first. And second, if we fast forward 2 or 3 years, what does trusted infrastructure look like if ZKPs are successful? And how does the world feel different in that scenario?
Yeah, that's a great question. So in the next year, we're building a protocol called Boundless. I mentioned these sort of 3 phases of development. And still, there hasn't been sort of an end-to-end solution developed for blockchain protocols to make it really easy to request zero-knowledge proofs and sort of service these requests. So for example, like if you want to adopt ZK today, in sort of that deployment phase, you have to learn how to run GPUs, potentially hundreds of GPUs, to service these requests for proofs, maybe tens of GPUs, which can be quite difficult. Also, if you're dependent on a centralized prover, you get what we call this like liveness, which is a security sort of paradigm, like this liveness threat, which is if your prover goes down, your on-chain system goes down effectively. And so we're building this protocol called Boundless, which makes it really easy for developers to request a proof from a decentralized network, P2P network, and sort of to service those requests and settle them onto any blockchain. So it's this verifiable compute network that adds the capabilities of ZK to every chain. We're really excited about that. We're launching sort of a mainnet beta in July, and we'll go to full mainnet in August with that. I think otherwise you can continue to look for dramatic improvements in performance. I'll make a bold claim. I think despite the fact that we've had 1,000x improvements over the last 2 years, we'll have another 100x performance improvement over the next year in performance. And so I think that you'll eventually, pretty soon here, be able to generate small zero-knowledge proofs on your phone, making it easier to build privacy applications and things like that. If we look out a little bit further across that 3-year time horizon, I think ZK becomes very similar to something like TLS, transport layer security. You guys don't think of those 3 words on a daily basis, yet every time you access a website securely, cryptography is protecting your information, allowing you to make payments online securely and safely without fearing the loss of your data. And ZK, in a similar way, will sort of just live behind the scenes and improve the things you can do and build online and on-chain safely, but the average end user will have little understanding or knowledge of its actual impact. And I think the other thing that I hope to see over the next few years is dramatic increase in institutional adoption for ZK. Mm-hmm. In my mind, ZK is actually the bridge that makes it possible for financial institutions to provide a sufficient level of privacy to operate on public blockchains. And so, for example, like just in the last year, the Bank of International Settlements, along with the Central Bank of Singapore, South Korea, they did a project called Project Mandala that used our ZKVM to develop a private payment system. Last year, there's a 30-page report on it. It was quite an interesting use case. And so I think a lot of those POCs will become real over the next few years. And yeah, ZK will provide this new option for verifiable compute outside of blockchain consensus. It's quite exciting.
Yeah, definitely agree. I think abstraction is the key to adoption, and that's what you guys are working towards. Awesome.
Absolutely.
Any key takeaway for our audience?
Key takeaway, yeah, ZK's here. You'll see all kinds of new use cases unlocked on chain, including in real-world assets. There's interoperability, in any sort of DeFi application, scaling blockchains. You'll hear a lot more about it in the next year and beyond.
Love that. Awesome. Yeah. Great. Thank you. Thank you very much. Thank you, everyone, for listening. And thanks, Brett, for sharing your insights.
Thanks.